Hello, this is Ben Leonard, and this is the fourth part of my introductory lectures on tribology. The first lecture was on tribology as a whole, the second was on wear, the third was on lubrication, and this lecture is on friction. It's entitled, "It's Kind of a Drag, Slowly Moving Through a Lecture on Friction." We are going to begin this lecture by going over the objectives. Then we will cover the different types of friction, including dry and lubricated friction. Then we will look at some special cases of static friction, stick-slip friction, and rolling friction. And then you may all remember the 3 laws of friction that they talked about in your undergraduate classes. And so we will go over them and do a quick check on how accurate they are. When we complete this lecture, I'd like for you to know the 4 common mechanisms of friction, to be able to explain the shape of the Stribeck curve, and also know what the Stribeck curve is, understand why static friction is so complicated, recognize stick-slip friction and know why it happens, and to understand that there are limitations to the applicability of the 3 laws of friction, and have some ideas about when those laws are not a good representation of nature. So what is friction? Friction is a resistance encountered when one body moves relative to another body with which it is in contact. So you've got 2 bodies moving against each other, and friction wants to make each of those bodies move in the direction that the other one is moving. So people often ask, what is the coefficient of friction of X? X can be some material, some coating, some lubricant. So we have to say friction, it's not a material property, the coefficient of friction. It's not a lubricant property, but it is a system property. For instance, if we take 2 steel surfaces, what is their coefficient of friction? It's a certain value. And now we add an oil in between them. That friction is going to change. Now we put them in a atmosphere under a vacuum where there's no oxygen, a pure nitrogen. That's going to change the coefficient of friction as well. So similarly, you take a silicone oil or silicone grease or oil, and you put it between 2 steel surfaces, very high coefficient of friction. Put it in between 2 plastic surfaces, and you've got a low coefficient of friction. What's the coefficient of friction of that lubricant? It's not a function of the lubricant, it's a function of the entire system. I've got this chart from a book called Guide to Friction, Wear, and Erosion Testing by Badinsky. I think it's a very good book. And he breaks this friction down into different types. And I thought I would begin with this just to go into a little bit more detail about friction being a system property. Also then to get us into what are the different modes of friction, or where does friction come from. So in rolling, we'll briefly cover this. Rolling friction, from left to right, it's a type of friction. Where does it happen? A couple examples: tires and bearings. What are the important factors in deciding what the friction is? The hardness and interface properties. Also, each of these types of friction will often have a different range of coefficient of frictions that appear in them. So next we go to solid on solid friction. Then in this mode you got metal versus metal, metal versus plastic, etc. It's controlled by the adhesion tendencies, how much the surfaces tend to adhere to each other in the system. We've got solid on solid friction with the third body. The third body is particles, or it could be a lubricant, some sort, that's in between the two sliding surfaces. So examples of the third body include dirt, wear debris, and solid lubricant. In this case, friction is controlled by surface properties and the nature of the third body. Next, for friction, you've got solid versus fluid. Examples: pipes, wind, channels, and rivers. This is controlled by the nature of the fluid, velocity, impingement angle. Then you've got solid on solid and fluid. Lubricated examples: lubricated bearings and seals. It's controlled by the separation fluid properties, sliding properties, surface properties. The lubrication regime. So here you can see how complex friction is. So mommy, where does friction come from? We've got a schematic of two surfaces sliding against each other. We know that there's going to be some friction resisting this motion. What is causing it? First question we're going to ask is this contact lubricated or unlubricated? Lubricated or dry? If it's dry, there's two primary mechanisms for resisting the motion. First is when two asperities collide with one another. So they either have to push one out of the way, break the other off, get pushed around it, or slide over it. That's asperity interference. Next, you have the two asperities contacting, and the like materials adhere together, and the molecules bond with each other, and that forms kind of a cold weld, which could be broken, which needs to be broken for the motion to continue, and it takes force to overcome that weld. While we are here, I will mention that when we talk about two surfaces coming into contact, we say that they're actually just contacting. Every surface is made up of a lot of asperities. It's not perfectly smooth. At least there may be a couple that are smooth on an atomic level, but in general, but those are only appear in research laboratories, the most advanced ones. But surfaces are made up of a lot of asperities, and so when the two surfaces touch, they're touching where different asperities come into contact. Next, we have lubricated surfaces. Here we can divide the causes of friction into two basic causes. The first is boundary lubrication. And here you've got surfaces which are touching each other, but there's a lubricant present, but the surfaces are touching each other through the lubricant. And what actually takes place is you have molecules kind of adhering, bonding onto the metal surfaces. And those molecules will form a thin molecular layer on the surface and prevent the base metals from actually touching. And that reduces friction in comparison to having no lubricant at all. That's boundary lubrication. The second is hydrodynamic lubrication. In this case, the surfaces are not actually touching, but there is a fluid in between them. and the fluid needs to be sheared in order to allow the surfaces to move. So you think about when you're moving put your finger in a glass of milk and turn it around, or you put your finger in a glass of honey and spin it around. It's a lot harder, even though to move it in the honey, even though your finger is not touching the wall of the jar or the cup. That's because of even though it's not touching the surface, you're trying to shear that fluid, trying to make that fluid move relative to itself. All right, so adhesion. In we discussed adhesion briefly. In this case, the disparities on the surfaces touch. And it's a little bit complex to get into, but everywhere an asperity touches, or pretty much at all asperity contact, the pressure is the yield pressure of the material. It's a very high pressure. Only a small percent amount of the apparent area of contact actually has metals touching, as the asperities touching, but at those few points where the asperities are actually in contact, you got very high pressure. So those asperities cold weld when in contact, and when you want the surfaces to move, you're breaking those cold welds, which causes wear to take place. In mechanical engagement, the asperities run into each other, means plowing through or riding over the opposing surface. So adhesion versus interlocking. Which is most important? Bowden and Tabor, two very famous researchers in England, and they did research, and they determined that adhesion is the primary cause of friction. And that's a generally accepted view today, although you never know. Science may turn up something else, and the battle could go back and forth. Since friction was first theorized about a few hundred years ago, the scientists have been arguing back and forth about whether adhesion or interlocking is more important. But in the current year, we think that adhesion is most important. And this also, the importance of adhesion also lets us know why friction and normal force are related. If you remember, the formula for the friction force is equal to the normal force multiplied by the coefficient of friction. And this is one of the arguments that Bowden and Tabor used. So normal force is equal to the real contact area multiplied by the yield stress. The friction force is equal to the real contact area multiplied by the stress to break a asperity apart. To break apart that asperity area. So that is why they are related. So now we're moving on to boundary lubrication. Boundary lubrication, as we discussed earlier, you've got the substrate, surface metal. Both of these schematics on this slide show this. And along that surface, you've got molecules adhering to it. Sometimes the molecules will physically react and form a permanent layer. Other times they will just be attracted to it and want to line up next to it. It depends on the type of additive that's used and temperature. Interestingly, even if you don't have lubrication, surfaces will the top surface will oxidize. So you have even in unlubricated contact, you do have boundary lubrication to a certain extent. And that is why if you have sliding surfaces inside a vacuum, the friction is usually much higher because no oxide layer forms on the surface of an unlubricated contact. So, so the base metals touch even more. But back on subject here to boundary lubrication, got the lubricant molecules bonding to the surface, and they keep the surfaces apart barely and prevent the base materials from touching. Hydrodynamic lubrication. The two surfaces are fully separated by the oil film, and so you're just shearing the lubricant film, and that lubricant absorbs the difference in velocity between the surfaces and provides pressure. With the two surfaces, gravity will want to make them touch. So the lubricant is applying a normal pressure to keep them apart, and it's also absorbing any difference in velocity. So within hydrodynamic lubrication, you've got two types of flows. One is Poiseuille flow and the other is Couette flow. With Poiseuille flow, it's driven by pressure. So there's a pressure that's pushing the lubricant between the surfaces, and the velocity then is zero on either edge of the flow, and it's the highest in the middle. An example of this would be with pipes. With Couette flow, it's driven by the velocity difference between the surface. So they're right next to both of the surfaces, the velocity is the same as the velocity of the lubricant is the same as the velocity of the surface, and you've got a linear change in velocity between the two surfaces. So we talked about whether there is adhesion or interlocking. Here we're talking about, do you have hydrodynamic or boundary lubrication? Well, it depends. In general, at high speeds and low loads, you'll have hydrodynamic lubrication, the surface is fully separated. And at low speeds and high loads, you'll have boundary lubrication, where the surfaces are touching. And interestingly, when you're in boundary lubrication, right on the figure we have on this slide is the Stribeck curve. And it shows the transition from hydrodynamic to boundary lubrication. So when you're on the left-hand side of this curve, low speed, high load, and also low viscosity, so something more like water as opposed to like molasses, you've got a high friction. And as you move to the right, you move more towards hydrodynamic lubrication, the friction goes down. This is because you start to get a little bit of hydrodynamic lubrication occurring in some parts of the contact, and that's called mixed lubrication. And then you'll reach a minimum friction where when all of the contact is separated by the lubricant film. Now you're in hydrodynamic lubrication, and at this point the friction begins increasing again. Think about this. It's harder to move your finger really fast in a jar of molasses or slower. It takes more effort. So even though your film thickness will get bigger, thicker and thicker as you move further to the right, you have more resistance to motion. So I mentioned molasses and water and the difference in their viscosity. So let's take a minute real quickly to go over what is viscosity. You've got a two surfaces moving, you can plot the shear stress versus the shear rate. The shear rate is the change in speed over the separation. The top figure you can see du dz. The different, for instance, the separation is 1 millimeter, and the difference in speed is 5 meters per second. It would be 5 meters per second divided by 1 millimeter. Then you've got shear stress. That's just the resistance. So as the shear rate goes up, the shear stress tends to go up, and that gives you Newton's law of viscosity. Tau is equal, which is the shear stress, is equal to your viscosity times the shear rate. And when you hear about a Newtonian fluid, that perfectly follows this law. So on the bottom you can see the shear stress versus shear rate for different types of fluids. Most lubricants are not exactly Newtonian. For instance, with grease, you can say, well, it's kind of similar to Newtonian, but it takes some stress to actually get it to move. It will remain constant. It will remain in place with a certain amount of stress. All right. Static friction. This is a very complex topic. Friction in general is hard to predict and get your mind around, and everything. All of the different factors which control friction make it a very difficult subject. But static friction is way more complex than dynamic friction. One difference between them is in a static friction. In static friction, you have a lot of small disparity contacts between the surfaces, whereas in dynamic friction, it's generally a few larger spots. In static friction, your coefficient of friction will change with time. The longer two surfaces are in contact, the higher the friction will be, the more force it will take to get them to move. Yeah, but the biggest change happens really quickly, and then the change slows down with time. Another thing that's a little bit complex is it's not cut and dry. When you start pushing on something and it hasn't started to slide, there's actually a little bit of displacement that's taking place. It's moving a little bit, and then eventually it breaks free, and that's where it's generally considered to slide. One way of maybe conceptualizing this static friction is more like a crack growing between a single body, and that crack is growing along the line where the two bodies come into contact. That's a way of thinking about the phenomena. Whereas in dynamic friction, you've got two moving bodies, and you're dealing with the resistance, how much force they're exerting on each other to resist their motion. All right. So when you look at static friction of lubricated contact, it becomes even more complicated than static friction of dry contacts. All right. So to begin with, you look over on the right. When a lubricated contact stops, you have a lubricant film separating the surfaces, and then that gets squeezed out of the way, and so that's a time-dependent process. And so the initial lubricant in the contact is going to affect what the static friction is, because after it's shut down, then when you're starting to move it again, you've got after it's shut down, you're starting to move it again, and you've got a startup problem, which is, again, a little bit complex. On the left-hand side, you can see a figure that I got out of a journal article. And we'll take a couple seconds to unpack this, and you can get an idea for how load, viscosity, and material are all interrelated in terms of the static friction. So we'll look at the bottom of those three graphs, and we take the material. We're looking at the normal load. Okay, so the normal load, as you increase the normal load, the static friction goes down. So that means your static friction is a function of your static coefficient of friction. So with the coefficient of friction, it's generally assumed to be constant with respect to normal force. Here we're seeing that is not the case at all. And then when we break down this information even more, and we put it up to, and we zoom in on the highest and the lowest loads, see that at the lowest load, as you increase your viscosity, this is the upper left figure of these three. As you increase your viscosity, your coefficient of friction goes up. And at the highest load, that's the upper right graph just next to that, as you increase your viscosity, your static coefficient of friction goes down. The exact opposite. You can see the two graphs are there right next to each other. So we're not going to go into why all of that is. In the paper they present some ideas, but as you can see, this is just pretty complex stuff. Next, we have stick-slip friction. Do you know what this is? I'm sure that you do. Have you often heard these really high-pitched squeals, such as fingernails on a chalkboard, or when you're sliding a desk across the floor and the feet just squeak on it? So that's stick-slip friction, that high-pitched squeal. What is going on at a really kind of fine level there? On the figure 8 here, a typical contact. This is, characteristic drawing. With time, as you start increasing your force, start moving, your friction goes up until you hit the point where you're going to increase your force, goes up, then you start sliding, and then the friction drops down to a constant value. Well, what's happening in stick-slip friction is you're going back and forth between sliding and sticking. So this happens generally when you're right on the border of sliding. You're just enough to get motion, but you're over the static friction. But typically what happens is you push over and you start to move, and then the force drops, and then you kind of stop. And then the force builds up and it pushes you again, you get moving, and then you stop. Go, stop, go, stop. All at a very fast rate, and that's what's causing static friction. So if you can really push a little bit further beyond the transition between stick and slip, you can generally take care of this. Rolling friction. With rolling, in general, with rolling, you're seeing much less resistance to motion than you are with sliding. Think about if you put on your parking brake and you try to push your car. Pretty much impossible, versus if you leave your parking brake off and you put your car in neutral, and you try to push your car. It's still hard, but you can do it. And there's two coefficients here. They sound like they could be the same, but they're both different. You've got the coefficient of rolling friction. This resists the rolling motion, and you want to have a low rolling friction. Comes from slip and deformation, and it's calculated by the resistance force over the normal force. The second is the coefficient of adhesion. This is the force, this is the resistance to skidding. You want high value, provides traction, and it comes from the surfaces adhering, because in rolling, the surfaces are, in perfect rolling, they wouldn't actually be sliding with each other. Wherever they're in contact, they're just staying stationary. Now the three laws of friction. Friction force is proportional to load. The first law of friction. The coefficient of friction is not related to apparent area. The second law. The third law is friction is not related to velocity. Rule number 1. Friction is proportional to load, to normal load. The verdict is generally true. This is predicted by Greenwood-Williamson theory, and the exceptions come from very hard materials, very soft materials, and cases where the real area of contact is close to the apparent area of contact. The second law of friction is that friction is not related to the apparent contact area. Again, this is generally true. And this is because, in general, the real area of contact, the amount of surface area of asperities that is touching each other, is generally independent of the apparent area of contact and only depends on the normal force. So the apparent area of contact is if you've got a ball and a flat. So when you just look at a contact and kind of two surfaces touching, you can measure the area that they appear to be touching. Real contact area is generally 1 to 0.01% of apparent contact area. Exceptions to this are viscoelastic materials, purely elastic materials, and materials with no yield limit. Rule number 3, coefficient of friction is independent of velocity. Well, there are many exceptions to this rule. Metals are mostly consistent with this law, but no materials completely follow the law. The reason for this is that as you increase the velocity, the temperature of the contact tends to rise because you've got less chance to dissipate the heat and more heat is being created. And the change in temperature changes the material properties. Also, this rule is not true for viscoelastic materials. So key points from this presentation. There are 4 main causes of friction: asperity welding, asperity interlocking, boundary friction, and hydrodynamic friction. Hydrodynamic versus boundary friction is described by the Stribeck curve. Static friction is time dependent and some motion occurs with any force. Stick slip is actually caused by high frequency intermittent sliding. And in rolling, low resistance and high traction are desired. So at this point I would take any questions, but since we're not together in real life, you're going to have to just talk to the computer. So thank you for your time, and I hope you enjoyed this lecture. Thank you.